Hello, this is Jake Abbott. In this video we're going to be talking about transfer functions. This is a topic that many of you are going to be familiar with from other classes that you've taken, and it basically uses the Laplace transform. In a state space controls class, most of the time we're working directly in time domain, and so we will just be working with differential equations that have sort of dots. These are derivatives with respect to time. But there's also this Laplace transform that you will have seen in classes on differential equations or in classical control systems. And occasionally we can make use of these Laplace transform concepts in state space too. So let's remember basically what these Laplace transform concepts were. If we had an equation that looked something like, we'd have x dot plus some variable p times x equals f, some forcing function. And now x dot is equal to some function of t, and x is a function of t, and x dot is the time derivative of x, and f is a function of t. Remember, these are all functions of t, and p is just some constant. Then we could take the Laplace transform of these functions. And Laplace transform, if you remember, it looks something like this. If I have some signal x of t, the Laplace transform, and the way we sometimes talk about that is we use this kind of squiggly L operator, Laplace transform of x of t. And the way we do this operation is we take the integral from 0 to infinity of this function x of t e to the minus st dt. And this is it's a mapping, and that ends up giving us this new function, which we'll call this new signal, and it's no longer a function of time now, it's a function of s. And in the Chen book, he uses a notation that's a hat, meaning Laplace transform, so I'll use that same notation. And so it's a way to take a signal in time domain and write it as a new signal in this S domain, and you can always go back and forth between these two, which is nice. So it's a completely invertible thing, and it lets you talk about it. It's still a signal, it's just encoded differently. And so you can go back and review other courses you've had in this, but one of the really big wins about the Laplace transform is in how it handles time derivatives. So if we were to take the Laplace transform of this signal on the left side and this signal on the right side, and we take the Laplace transform of both sides, the Laplace transform of this signal on the left side is simply the Laplace transform of the x dot plus the Laplace transform of the px. And the big win in the Laplace transform, the thing why we even bother to learn it, is really how it handles the derivative. So this time derivative, x dot of t, simply becomes s times x of s. So basically a dot becomes an s, a double dot becomes an s squared. And then you've also got this initial condition, and this is actually the initial condition in time domain, so there's no hat here. And so this is how an x dot becomes, and then constants don't do anything, and x of t, by definition over here on the right, simply becomes this function x of s, and then f of t, by definition, becomes this function f of s. So this is the Laplace transform. So the cool thing is time derivatives simply become algebraic s's, and each time derivative is another s. Now this alone is kind of cool, but it's not super useful. But the really, really huge win with Laplace transforms is what happens if we say, if we assume x at 0 is equal to 0. If we're willing to make that assumption that the initial condition is 0, then this equation simplifies to this equation. And I mean, the thing you should notice about the original equation is, on this left side, everything in the equation has an x hat of s, except for this x naught term. So if we get rid of that x naught term, now everything on the left side has that x hat of s term, which means we can factor it out. And all of a sudden, this looks like s plus p times this function x of s equals f of s. And from there, we were able to talk about this thing known as a transfer function. And a transfer function is a relationship between an output signal written in Laplace domain versus an input signal written in Laplace domain. So it's a ratio of an output to an input. And that thing, in this case, if I bring the f down here and then I bring this down here, looks like this transfer function, 1 over s plus p, and we call p the pole of this transfer function, and that pole completely defines the stability properties of this signal. And the cool thing about that is the transfer function is completely system dependent. This transfer function represents the system. It's completely independent of the input. This is the input signal. And the input signal now is completely decoupled from the system. I can talk about the system as this transfer function 1 over s plus p, and that is true regardless of the input I give it. Whether the input is a 0, whether the input is a step input, whether it's a sinusoid, it doesn't matter. This transfer function is the system. And you don't really get that with time domain differential equations. And if you think about it, it's very difficult for me to talk about the system here independent from the input and from the output. Everything's all coupled together through this differential equation. So the transfer function is very powerful in that way. Well, it turns out that for multi-input, multi-output systems that we're looking at in this course, we still can maintain this idea of transfer functions. So let's look at that. So we're going to be looking at equations that look like this in general. So we have a vector, x dot of t, equals a matrix A times a vector x of t plus a matrix B times a vector u of t. And then we have this vector y of t. And of course I'm saying vectors, but it could be these vectors are 1 by 1 vectors. That's totally fine. So it's scalars. C times x of t plus d times u of t. And I've written A, B, C, and D as linear time invariant systems. They're not changing in time. So this is the system we're starting with. So we're going to be able to do this same thing with the Laplace transform, where we can take this vector x dot of t and write it as s times, and now I'm going to have to use this notation. I'll use x vector hat. So the hat means it's a Laplace transform of the time domain, but it's still a vector. And the dot becomes an s, and that equals a times this x Laplace transform vector plus b times this u Laplace transform vector. And so by definition what we're saying here, when I say this vector x of s like this, what I'm really talking about here is a vector that's an n by 1 thing where each of these individual elements is the Laplace transform of that one signal that's in the time domain. So the Laplace transform of x1 of t, the Laplace transform of x2 of t. It's sort of how you imagine it would be defined. It's just term by term. So, excuse me, I missed one important term over here, which is I need my initial condition equation, x of 0. Now, just like before, if we're willing to make this assumption, assume that this vector x of 0, the initial condition vector, is the 0 vector, meaning that every single element in our state vector is 0. If we do that, then this equation simplifies to x hat of s equals a x hat of s plus b u hat of s. And then I can bring this a over to the other side. Actually, I think for now, let's for a moment not make this assumption. Let's go ahead and keep track of this. Okay, so I'm just gonna kind of forget this line. Let's not assume this yet. Let's wait. We'll assume it in a second. It's kind of cool to keep track of it, I think. So we're back up to this equation. So what I'm going to do is I'm going to bring this ax over to the left side, and I'm going to bring this x naught over to the right side. So I get something like this. S x hat of s minus a x hat of s, and then I've brought the x naught over to the other side. And notice this isn't a hatted thing, so this is actually the initial condition in time domain, plus b u hat of s. Okay, now it's tempting here to do the same sort of trick we did with the scalar differential equations and factor this x of s out and do something like this. S minus a x hat of s. The problem is this s is a scalar thing. It's a 1 by 1 thing. And this a is an n by n matrix. So you can't add a 1 by 1 thing and an n by n thing. So this doesn't make any sense. So I can't factor out like this, right? That doesn't work. But what you do is you recognize this identity here. This is a vector, an n by 1 vector. And if you take an n by n identity matrix, n by n, and I multiply that by any vector v that's n by 1, the thing I get back is the exact vector. And remember, an identity matrix is, it looks like 1, 1, 1, right? This is a 3 by 3 identity matrix. So it's pretty easy to prove to yourself just doing the matrix multiplication that this is true. So I can take any vector, times it by an identity matrix, and I get the same vector back. So this is a perfect equality. So if I come back up to this equation here, I can convert that into Si. This wasn't actually the perfect analogy I needed. Another truth is if I take I'm sorry. I'm doing this correctly. So when I take this s here, it's not the s I'm multiplying by the I, it's the x. So I replace this x with this ix, where in this case, here's my analogy, iv equals v. The vector here is this x. So I've replaced x with ix. So it's a direct equality. There's no problem there. And then now equals ... And now this is a 3 by 3 thing. If I take an identity matrix, or I shouldn't say 3 by 3, I should say n by n. So this n by n identity matrix times a scalar s is just another n by n matrix. So now I really do have an n by n thing here and an n by n thing here, and I can factor that out. So I can write Si minus a, and now I have an n by n minus an n by n. I factor the sx out, and that's equal to x naught plus bu. Okay, now in the scalar case, we divided by this. It was in our scalar case on the last slide. It looked like s plus p, and then we divided by that s plus p to get 1 over s plus p as our transfer function. Well, we can't divide here because you can't divide by a matrix. Instead, what you have to do is you have to take the inverse of the matrix. So we're going to take the inverse of this matrix, and we're just for now going to assume it exists. So I'm going to take the left inverse. So I'm going to multiply this side by Si minus a inverse, and I'm going to do the same thing over here. I'm going to multiply this side by Si minus a inverse. So I'll go to the clean slide and I'll summarize this. So I'm going to have Si minus a inverse times Si minus a times x hat of s, and that's going to equal Si minus a inverse times this whole quantity, x naught plus bu. So now when I take any matrix times its inverse, I get the identity matrix. So this whole thing here just becomes the identity matrix. But when I take a vector times the identity matrix, I just get that vector back. So this whole thing just becomes x hat of s. And that equals this thing here. So I can write this as Si minus a inverse times my initial condition plus Si minus a inverse times b times my input function. Now remember, this u is some like p by 1 vector, and this x is an n by 1 vector. Right? These are different dimensions from each other. So basically, if I look at my signal x of s in Laplace domain, it's basically my initial condition passing through this transfer function matrix. This is an n by n thing. And then I have my inputs passing through this matrix, and this is an n by p thing. And this is true, so you basically can say my signal x is some combination of my initial conditions moving through this thing and my inputs moving through this thing. And this si minus a is in both of them, and we're going to find, this is really the kind of the system itself. It's going to fundamentally define the system in terms of its dynamics and its stability. And then this b is some sort of thing that sort of maps the inputs into the system. I mean, that's kind of a really simplistic way to look at it. And now, if we assume the assumption I was trying to make earlier, that our initial conditions are 0, then this whole term goes away, and we have this much simpler relationship here. So then if we do that, we have this equation. X hat of s is equal to this si minus a, that whole matrix inverse, times b times u of s hat. And then if we use this equation that we had, y is equal to cx, so this is y of t equals cx of t plus du of t, and we take the Laplace transform on both sides, we have this function y of s equals cx of s plus du of s. And now we have an equation for what x is, and if we plug that in right here, what we get is we get an equation for y that looks like y of s equals c times x, and this is x, so c times x, si minus a, inverse b, u of s, and then plus du. And so both of these terms, the left side and the right side, both have a u, and we can factor those out. So I have this vector of signals y of s is equal to this big thing c times si minus a inverse times b plus d. This whole big thing, I've factored my u out. And what is u? That's a p by 1 vector. And this y is some q by 1 vector of outputs. So this thing here, which we call g of s, is some big q by p transfer function matrix. And so it's a big q by p matrix, but each element in it is itself a transfer function. So it's a big thing like this, where I have all these little transfer functions, g11 of s, dot, 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 to g1, let's see, I have q by p means q rows and p columns, so this is 1p, and then this is g q1, and then this is g qp. These are supposed to be g's. So it's this big matrix of transfer functions, scalar transfer functions that you're used to thinking about. So you can basically, when you think about it, if this is mapping a bunch of inputs, u1 of s through up of s, and this is y1 of s through yq of s, then you can think of, what is this transfer function? It's the transfer function from this input to this output. Well, what's this transfer function? That's the transfer function from this input to this output. So each one is a well-defined transfer function from one input to one output. So each of the individual little transfer functions are scalars, meaning they're single input, single output transfer function. but we call this big thing here a multi-input, multi-output transfer function matrix.